So, this is a pretty important video. It's in regards to, I'm introducing the idea of a stress-strain diagram and all the important features that you notice over there. So, say if I have myself, again, another specimen of a material, be it glass, metal, whatever. I apply myself in a force as usual, and then we notice all the different effects of it before it breaks. So what I'm going to do is at every moment, imagine if I have a computer or a machine that does this, at every moment what it does is that it measures the force, and then convert that into stress. Just divide by the cross-sectional area, the original cross-sectional area. So that's just a factor of something. Yeah. Measures extension, and then convert that into strain. And then what it does is that it plots stress versus strain. This is the y-axis, this is the x-axis. Yeah. So say if I sample this for a metal. Generally metals will have like this characteristic shape, that's why I'm going off them. But yeah, so stress, strain. Okay, so first what you notice of materials is that it starts exhibiting this straight line feature. Then what happens is that it starts going into a rounder curve, and then it starts reaching like a peak, and then it'll like just drastically stop. Sometimes there's an error with the machine where it just like drops down and then just goes across. That just means that the object is broken. But yeah. So going into the main features of these diagrams, because these diagrams tell you a whole lot of information about the specimen itself, or the material, because again, material science. This might be a longer video, so strap your seatbelts. So, taking this straight line section, the straight line section is what we call the elastic region, where it exhibits elastic behavior that I mentioned last video. So here is where we apply Hooke's law, where we had the stress is equal to the modulus of elasticity times the strain, or I can just say E is equal to stress and strain. So it's literally that they're proportional to one another, and that's why you have the straight line part. So it's literally the slope of the line. Yeah, the slope of the line is the stress on strain. Yeah, and so that slope equals your modulus of elasticity. Yeah. Then you're gonna hit a point, well, not exactly a point, but like where it starts deviating away from being a straight line. Yeah, starts going away. Now what we have to do is we have to like decide a point where we can say, okay, from here it's not really elastic anymore, and it starts becoming more plastic. So the straight line region is definitely elastic. The part that's not straight line is definitely not. Yeah, and that's what we call plastic. So to a certain point, we have we call a point a yield point. I'm going to call that point here-ish. Okay, and so then that's what I call my yield stress. Actually, I'll project that across. This is my yield stress, and this is my yield strain. Your yield, pretty important definition, is like your yield stress and strain is when noticeable plastic deformation occurs. So if you let it go, you will actually notice that there's a difference. So because if you just take like the tangent line, it kind of just slowly deviates away, so there's no obvious position. So what we do in practice is that we offset this from the origin. We offset it by a certain amount, might be around 2%. like 0.02 or 0.2%, depends on the amount that they specify. And what you do is that you project it so that's parallel to this line, so parallel to the line, and see where it intersects. And see where it intersects the original curve, and that's what you call your yield stress. Yeah. So important point, because that's like the position between plastic and elastic. Generally, when you make materials or do it in practice, you always pick a material that is always in its elastic region, so that it never goes into something plastic and it doesn't get messy. Yeah, you can always apply Hooke's law again and again. Anyway, in extreme situations, we also want to consider this maximum top point, and that's the maximum stress that it feels, right? So this is what we call the tensile stress. Tensile stress. But some people like to be extra, and then they call this the ultimate tensile stress. Depends on who you're talking to. Same thing. Yeah, it's the maximum stress that the object will ever experience. So yeah, this section was what we called elastic. This section across all the way up into breaking, that's plastic. So from this ultimate tensile stress onto this fracture point, the material starts to exhibit like an effect that we call necking. And no, it's not like like something else. It's just necking. It's the thing it's literally like getting into a bottleneck. So the cross-sectional area gets thinner and thinner, and that means it's just a weaker object as a whole. So as it thins, it comes down and points down until it breaks. So this point is fracture. And this phase is what we call necking. Yeah. Yeah. I think with that, I've labeled every important point on here. Yeah, with that, I'll finish off the video.